well, CFT in 2 dimensions this week. And all using my words, we'll see we're going to scratch the surface of CFT because there's not much we're going to cover in 4 days. And we'll on the surface. And of course, that the first thing we should ask the question is that if we spend 5 lectures and already studied in any dimension, by proportionality, we should spend 0 time on each individual dimension, and while we're spending another whole week just on b equals 2. So there should be some motivation given. I'll try to be motivated. So first of all, well, look, an answer is that because we can. So this is a dimension that we can find a lot of solvable series. This is where people get very excited and says, look, I have a CFT and I can classify all the CFTs that have finite primary operators, and I can really just completely solve it. By completely solve it in a CFT sense just means we can find all the correlation functions you are ever interested in. Okay, one thing that CFT is very popular is because, in QFT you learn something action, and probably you learned a lot and suffer through some homework to do perturbation expansion, And the advantage of CFT is, okay, let's forget about the action. I don't even know what's the action. But I can calculate all the correlation functions. So who cares? Okay, so that would be one motivation. And second motivation will coming from string theory. And the idea is simple. It says that if you start a point and you track it as time evolves, you get a word line. So if you start with a string, and it will sweep a surface, so which is 2-dimensional. And you were like, why do I want to learn string theory? Well, then you have to wait Davide to give you the motivation for that. There were lots of debate about if it's physics or not. But for me, that's fair enough. All right. Okay. So let's continue to say, what's the plan for the next 4 days? Well, the first day, we ask the same question. It would be like, it seems we have already done it, but in 2-dimensional, as you might have heard from last week, it's very special in the way that it has infinite symmetry, and which also tell us how come that we can actually just solve them without actually have any physics. Based on it, there's just some mathematician just come out and says, look, all CFTs, this is a class of the infinite number of CFTs, and that they're all solved. So the first day we'll ask same questions, is that what is a conformal transformation, which you have seen in the transformations. You have seen in other dimensions, they are characterized by some generators, infinitesimal transformations, And the interesting thing today would be they are infinite dimensional. And, well, of course, then we'll study the algebra of it and introduce some players. And tomorrow, this is what we discussed today, at least the majority today, is really just about the geometry. It has no physics. It's just there are some space-time transformations, let's just say, what algebra gives you. But tomorrow, we're going to study physics and then learn something called Virasoro algebra, which is probably you heard a bunch of times. And it's related to the energy momentum tensor. Hey, there's the physics. And we will spend the whole day tomorrow and land on it. There are some important concepts such as reduced quantization, you might have heard of, and OPE, you definitely have heard of. And we're going to try to land on this. And after you get the algebra, if you recall, quite a few months ago, when we find the algebra, you want to build a Hilbert space and study the states. So that will be the topic of the third lecture. We'll build the Hilbert space for this Wilson algebra. Makes sense? It's a logical things to do. And the last day, and there is some miracles going on, and we'll try to get to them. But eventually, what I call this is how to cook up your own solvable 2D CFT. It's like a step-by-step process. Well, of course, you have to do it in infinite steps. But fortunately, we have mathematicians who have done it, and then we can look at something called minimal models. Okay, that's that. And so today, we'll look at the conformal transformations, and we'll look at the algebra. And then, importantly, we want to connect to more than 2 dimensions. And why is it interesting to restudy it? And since it is one of the infinite many dimensions after all, so there must be some connection we can seek after, which is kind of fun. And then the rest part should be a review of how powerful conformal symmetry is. So we'll reintroduce primary fields, which you must have heard of a bunch of times. And then we will take a look at the energy momentum tensor again. And since we don't even have action without that, the thing that I can sort of say for sure about physics is there must be an energy momentum tensor. Who knows what else do we have? Well, apparently we have some primary fields. Okay, but that part should not be surprising because you have already seen it once. Twice, because you also seen it before. Anyway, okay, before we get started, I guess we should recap what we learned from last week. Since it's like a recap from, last Monday and Tuesday. So it might make sense for me to write it again. Is that the conformal transformation is defined to be a transformation. We get x to x tilde such that if we measure the distance, we realize that the matrix is almost the same, called conformal flat, except there is this conformal factor pop out. Locally, it's flat with some distance factor, and they preserve angles. So that's just the definition. And then, remember we see that, as always, we like things to be manageable, so we stay infinitesimally to identity and only study the infinitesimal transformation of this. And hopefully this doesn't surprise you anymore, which is nothing but the conformal Killing equation. Okay. No surprise? Something we already learned. And then the third thing, what we learned is for a CFT on D dimension, we can cutely organize our generator in the following way. Is that this is where our Lorentz sits, and there is some linear combination of translation and special I'll just put tutor because it's a linear combination of the ones we define. And you see this guy is at -2 or -1. And this is between 0 and d -1. And similarly, you have the transpose up there. Some other linear combination. Okay. And then you have something here, which is the dilatation. Okay, but the idea is this is all the generators of a conformal transformation, which has the Lorentz, the translation from Poincare, and the new thing we find out is the dilatation and the special conformal. And if you organize this as that, you can say, well, this is just another, M mu nu thing. It has the same property, they transform the same, and hence you claim that for conformal field theory on d dimension, let's keep it all Euclidean, then you get a group of SOD plus 1, 1. Here's a fun fact. This group happens to be the isometry for ADS, D plus 1. So, as somebody who is willing to take a leap of faith, you could just claim this is our first taste of ADS CFT correspondence. Well, they have the same symmetry group. Okay. And that's what we learned. Okay. Now let's really get the class started and come back to d equals 2. So what happens in d equals 2? So disclaimer, I'm going to claim that I'll take the Euclidean signature and hopefully everything works out if you just do some Wick rotations. So from now on, our metric is dirt mu nu. Define it in the Euro way, like I did. Okay, so let's do it. We have the formula right there. So our conformal Hilling equation reads as, I'm just copying it, taking d equals 2, I get this guy. Okay? But since when e equals 2, mu runs from 0 and 1. So I can literally write out what does this mean. Write down all the components. Normally it's not recommended, but when you only have 2 things to run through, it actually make your life easier if you just write it out. And this is gone. And the other one is just you switch the index and you get a 0 on the other side. So if I summarize it, it tells me partial 0, cosine 0 equals partial 1, cosine 1, partial 0, cosine 1 equals minus cos 1. Right? So that's the 2 equations we need to solve. If we solve it, we claim we understand all the conformal transformations, at least on the infinitesimal sense. And remember, the solution of this 1D is bigger than 2 is kind of long. So
the second one is D1's 0?
Yes. Sorry. That's important. Okay. Do anybody recognize this? Let me rewrite it. So this cosine 0 and cosine 1 is just 2 separate functions, right? So it's really a function of xy, which has 2 components. I call one of the component u of xy, and the other component v of xy. And that is really saying partial u equals partial x equals partial v, partial y. The other one says partial u partial y is minus partial v, partial x. Does this ring a bell now? And what is this?
Cauchy-Riemann.
The Cauchy-Riemann. Very good. Cauchy-Riemann says that, we must be working with a holomorphic function. So that tells us, look, in 2D, it's a plane. And we should really live on the complex plane. Which makes sense. You do have like a whole week of lecture to study the complex plane. And so let's employ all our knowledge about it, which makes it easier. But if, like, this is a time when we harvest the crops you grow on the complex plane, like barleys and wheat. You can brew beer with them. The flavor is probably complex. Okay, so what we learned about complex plane is that we should really combine this Cauchy0 and Cauchy1, and then this function, well, okay, there is another leap of faith. So this is what we solve the infinitesimal conformal Killing equation, and the result is that if fz is only a function, if fdz bar is only a function of fz, then it's really a conformal transformation. So conformal transformation is described by all the holomorphic functions. They can even have poles, then they have some other fancy name. But I can't pronounce that one. Okay, it's a holomorphic function. So this tells us, and then we can check if the leap of faith is correct to take by looking at the definition that it is not infinitesimal. So there's a cute little exercise you can show this afternoon that this thing is our infinitesimal length square. And after you do this transformation, you realize our metric is off diagonal. It will just look like this, with either 1/2 or 1 in front, which I can't remember. But it's proportional to this. Okay, so now, if we let z goes to fz, z bar goes to fz bar, up the bar there, then dz bar goes to dfz, dz, df bar z bar, dz bar, the other way around. Okay, I'll just put a -1 on top of them. So then now there's dfz, dfz bar. The idea is, yes, this would work because I can read off whatever is in front of this as the conformal factor. So we propose any holomorphic function is a conformal transformation. It's indeed one because it can put in this form, and we have we can find the corresponding conformal factor. Yeah.
Can you put the
board on? Yeah.
bit?
Yep. Sorry.
That's good.
So this line element normally has many terms, but since we're living on a complex plane, a flat complex plane, that's all it is left. You just have to figure out what this one term does. Hey, to transform with the chain rule of calculus and pick up some factor, which we can call it the conformal factor. The important thing is no terms with dz, dz, or dz bar pop out. It's still just this one term. Okay, so we found all our conformal transformations. So, done. Next step, is, of course, to study the algebra. We have some symmetry, and then there must be some Lie algebra related to it. And let's say again, we decided to hide back to our next to identity thing. So we'll say it's z plus some infinitesimal things. And then we can expand this. It's, well, anything can be expanded like this. It's just some Laurent expansion with some coefficient. At this point, I will assume this guy's all small. So that's our solution. Right? You can do this with anything. Okay, very good. And what we learned from last week is that we can just take a vector field, perform the commutator of the vector field, and read off the algebra. Let's be even more specific. Let's take only one of this expansion term is non-zero and everybody else is zero. Just make our life easier. Otherwise, I have to have this sum sign all over the place. And then conventionally, it's defined with a minus sign. Okay, sorry. I need to define this thing. So from now on, partial just means partial respect to z. Partial bar means partial respect to z bar. It's just chalk saving. So recall, that's how you define a vector field. You just multiply by this partial. Okay. And the minus sign is a convention. Then we'll get to the nice conventional weight algebra. So now we have it. We have a bunch of vector fields. Now we just need to calculate the commutator. So it's Ln, Lm. Ln and m can be anything between minus infinity and infinity. Integer, but otherwise, no other requirement needed. So this is the commutator. Since this is a commutator, I have another term just switching them. Okay. So the only non-vanishing term is when this partial acts on this, because the other one would be canceled by the second part of the commutator. So you get Zn plus 1 for the year 1 calculus. And then the other term, I can just copy it and switch m and n. And you say, let's collect the term together. Okay, this is down to high school algebra. Now I can happily put a minus sign back because that's how it's defined. And then say this is nothing but Ln plus n. Ta-da! So we'll have the algebra. And then, I'm not going to do it, because it's very easy to convince yourself the anti-holomorphic part must give you the same thing, except everything becomes barred. And it is also very easy to convince yourself these two sets of things don't talk. So we have the complete weight algebra. And we see the major difference between what we have now and what we have last week is, well, first of all, they look really pretty. And also, they are really infinite dimensional. We have an infinite amount of generators. We actually have two sets of infinite number of generators. And there's one set, there's the other set, but they don't talk to each other, so they are like a direct sum. Okay? Any questions so far? All agree with me? We got to the algebra? Okay. This algebra is sometimes called the local conformal algebra. And then, of course, if I say that, you should say, okay, there must be something called the global conformal algebra. Otherwise, why this one has a special adjective here? The reason for that is when I first write down this, you guys should be suspicious. Okay, let's take a look at our generator. This is varisome at some points on our complex plane. Sometimes it doesn't make really sense to do it. And where does it start to not making sense? Where could it possibly go wrong on a complex plane? If Z is just a random point on a complex plane here, now there's no trouble. But when you take Z to some power, where could it go wrong? This power can be negative. N is really literally all the integers.
No.
Okay. So where would it go wrong?
0.
0. So is this generator always defined at 0? Of course, if you say 0, then you might worry about what about infinity. It doesn't quite make sense to take infinity to some power either. Okay, so is R, well, in English, boundary. Is it defined? You should ask the question. And then you should also be convinced, as long as there's no problem with the origin, no problem with the infinity, then indeed this is globally defined. And hence, there is this local thing. So let's try to find the global conformal algebra. Okay, so there are two cases. Let's study case by case. At Z equals 0, so we shall demand n plus 1 bigger or equal to 0. If you take a positive power, you get 0, no problem. If you take a negative power, we run into trouble. So this tells us when n is bigger than or equal to minus 1, we are happy with origin. Okay. At Z goes to infinity. So like, how am I supposed to study Z goes to infinity? Well, we are studying conformal transformation. So there is one very nice conformal transformation will make infinity studyable, which is
The inversion.
the inverse. Very good. So we shall instead study W equals 1 over Z. And hence, this guy goes to 0, and use the same argument to figure out how this thing is defined at infinity. So let's do more elementary calculus. Says partial W must be partial Z, partial W, partial Z. And this must be minus 1 over omega W squared, partial Z. And then the thing we worried about is Zn plus 1 partial Z, which goes to 1 over W to the n plus 1, and with W squared, or minus W squared, partial W. And then let's combine these things together, which is W to the minus n minus 1 plus 2, so it's minus n plus 1 partial W. Okay. So this thing must be like this, which tells us now we're at 0. So we demand its power is bigger than 0 again, bigger or equal to 0 again. And this gives us n should be smaller or equal to 1. Now we're done. There are only 2 problematic points, and we fix it. We conclude that if we only look at L minus 1, L0, L1, L bar, the corresponding bar guys, the 6 guys. The number is 6. Then they are globally defined. So if you only look at this little part of the algebra, that's the global conformal algebra. So let's do some sanity check. There are 6 of them. Why does the number 6 make sense? Why should we expect 6? Well, in 2D, and remember we have a nice formula there, tells us what 2D should have got if it doesn't happen to have infinite dimensional algebra, right? So what's the conformal group on 2D?
SL2C.
SO.
SL2.
Yeah, we'll get to there later. But if you just look at that, if you suppose, so that says at D equals generic D, you should have got SO D plus 1, 1. You're going 10 or 15 minutes ahead of us. We'll get there. But if you just say, I plug D equals 2 there, I should have got SO3, 1. And if you calculate how many generators from here, fun fact, this number is also 6. So it's not totally surprising that in 2D we have an infinite amount of symmetry, but the symmetry that makes sense everywhere is actually the symmetry we found last week, which works for any dimension anyway. Okay, so let's get to Surya's point that there is a SL2Z somewhere, which I think he will be the correct person to ask why these two groups is the same. Okay, let's take a look at our infinitesimal transformation corresponding to these generators a little carefully. So I guess I could call this guy epsilon minus 1. So epsilon minus 1 is just the transformation corresponding to L minus 1. So I'll drop the operator partial part. So this one, by definition, is A minus 1, Z to the minus 1 plus 1, which is Z to 0. So it's A minus 1, which is a constant. So what did we learn about a infinitesimal transformation, which is a constant? So what is that?
Yeah. The translation?
It's the translation, of course. You move something by constant. This is the translation. Very good. Let's look at epsilon 0. This is A0, Z to the 1. And what is this one? It's something multiplied by Z by a constant. So
Dilatation.
the dilatation. Well, you sort of get tricked. It is indeed the dilatation, but plus something. Because normally these guys are real numbers. We're living in an uncomplex plane. So I should have write this like this. So if you manipulate, do some not complicated manipulation at all, a simple exercise shows if you combine the two L0 and the L0 bar, you get something R partial R, which is indeed the dilatation. And then if you look at, okay, there should be a proportion with some constants needs to be tracked. But if you look at the difference, this is proportional partial phi, which is a constant. It's a translation in the phi direction, which is a rotation. So actually the rotation, which we only have one because we're in 2D, also hides in this term. And it's not directly related to L0 and the L0 bar, but you have to do some combination. Okay? But it's convincing. Come on, it's r times e to the. It's very convincing. It's dilatation, but since there's an angle hiding there, what could it do? Okay, so, well, by process of elimination, what do you think epsilon 1 would correspond to? We have translation, rotation, dilatation. And the only other thing we know, hopefully, you remember, is the special conformal transformation, which looks quite ugly last time. This is A1z to the 2. Okay. It looks prettier. And I was like, how do you know this is special conformal transformation? It doesn't really look like the thing that I remembered. Where did all this prep go, right? Okay. Let me continue to do my leap of faith thing. Says that this is actually the transformation. You always have the original thing, and then you add some infinitesimal part. I mean, this is not hard to convince that that is true. And then what I'm going to do is I'll do the inverse expansion and say this must be proportional to 1 minus A1z. Well, it should be equals to this plus some bunch of things. So there is some even smaller things that the finite version of this transformation is this guy. It's just a small expansion of 1 over 1 minus x is 1 plus x. There's nothing fancy, right? So I'm just saying, this guy, the finite transformation for that guy should look like this. And you're like, okay, sure. I still don't recognize this as a special conformal transformation. I know the finite form of a special conformal transformation still doesn't look like this. So how do we continue to, but we know it gotta be that one. So how do we show this thing is special conformal transformation? The thing we remembered last time is that the special conformal transformation is some transformation combined with some other transformation and combined with even more transformation, right? And that one, we already used it, the inverse. Let's do the same trick again. So a w equals 1 over z and see what happens. So this is d theta. This is a proposed transformation. Let's see what happens if we do that. On the left is simple, we just inversed it. And this one is 1 over w minus a1 over w. And you do algebra to make it look prettier. So it looks like this. And then you get rid of, you flip it again. So indeed, this transformation corresponding the inverse of this guy get a translate. So it's indeed, you inverse it, translate the inverse back. And this is what you get. Now, I'm convinced enough that since P mu is equals to I P mu I, so this must be the special conformal transformation. So good. Let's do sanity check again. So there are two of these guys, because I didn't do the z-bar guy. And there is two of the translation. I also didn't do the z-bar guy. And then the claim is that the two in the middle combined to give you 1 dilatation, 1 rotation. So 6. So very good. Now we are very happy to claim, indeed, the subset of our local conformal algebra, which does give us 6 generators, and they do form a global conformal algebra, which is nothing but the conformal algebra everybody has. And even corresponding to the very specific transformation we learned, which is nice. Now let's get to the point that has been raised by Surya, is that if you look at the form of these transformations, it looks like this. The most nasty one looks like this. And the other one is like shifted by a constant, shifted by something proportional to state. So you can show that there is actually a neat form of writing all the global transformation into AZ plus B over CZ plus D. Okay, this afternoon you have a very, 30 seconds exercise to identify what's the corresponding ABCD for each of them. But it should be very clear that we're just missing by some proportional constant. Okay, about this, there should be, we need to put some constraints on these constants, ABCDs. Well, first of all, before we have 6 generators, which give us 6 real parameters for the algebra, now we jump to 4 complex numbers, so something must be wrong. Okay. Now the thing is, if you look at this, if I multiply everybody by something like lambda, it's the same transformation. So the first thing you should get rid of the overall constant. Or the other way of saying it is, look, there's 4 numbers. It's not that a leap, say they form a matrix, 2 by 2 matrix. And then, and the nice thing to demand is we demand the determinant is 1, which could certainly help us so that you can't freely rescale them. So now we go from 4 complex number down to 3. The number of real parameter match, and we're very happy. And this is a 2. This is a special. Remember, whenever we encounter determinant is 1, we call it a special. That's where the special unitary, special orthogonal come from. So it must be a special. And then it's a matrix, which comes from linear algebra. So this is the special linear algebra in 2 dimensions with complex, which is what Australia said 15 minutes ago. So these matrices indeed form a group. And you can check with the group definition that they form a group, and this is the name of the group. And there's one last catch, is that if I send m goes to minus m, I just add a minus sign in front of all of them. It's still the same transformation, and that I can't get rid of, because I'm changing everything by minus. So which means this is a double cover of the group we want. So this thing that describes the global transformations we just see is this guy. And it's very interesting. It's a mathematics fun fact that this group is indeed has the same structure as SO31. And which in the tutorial we can let Dallimot show you that how you can say that intuitively they are the same group. Okay. So let's summarize that we have seen all the conformal transformation. They're nothing but any holomorphic function. We have to expand it, find an infinite number of coefficients and an infinite number of generators. But fortunately, the commutator of them, the algebra is, although infinite dimensional, but it looks very nice and simple. And further, we say, let's compare to what happens in the bigger than 2. We indeed find the 6 generators that are corresponding to the global conformal algebra, which is satisfied by conformal symmetry in any dimensions. So we're basically done. And as I said, the last little bit, we're going to do some reminders, which is, okay, recap part 2, is that what we learned from last week is conformal symmetries are very powerful. But before that, we have to introduce our VIP players in the town, which is the primary fields. Okay. So let me try to explain it word by word. It's called a primary, which means it's very important for the following reasons. Is that in the last lecture, we'll see something miracle. Says that, in the second to last lectures, we'll say the first thing is that if you are not a primary and if you live in the CFT, you must be a descendant of the primary. And in the last lecture, we'll say the miracle is any correlation function with some descendant here is determined by some differential equations of the primaries. So if you know the correlation of the primary functions, you will figure out what's the descendant anyway. And at the end of last week, you also learned that 4-point function will put some crossing symmetry constraints on your CFT data. Okay, maybe I should write it. So there is some CFT data, which is basically the dimension of the operators. There are some sets of them, and there are some structure constants. And then the idea is the CFT data plus the crossing symmetry will give you any correlation function of primary operators you want. And since the descendants can be related to the primary operator, you basically know everything. And then you will also say there's a second miracle too. Says that since we have an infinite number of symmetries, so we can really constrain ourselves down to only finite number of primary fields. And now we're really done. We have a finite number of primary fields, and also the dimension of them are determinant. We literally solved it. So that will postpone until the last lecture. So now I explained primary. So now I have to explain fields, because it does mean different things than what we learned from QFT. What you call fields in QFT is you have a scalar field phi, you have a fermion field psi, you have a vector field A. But in CFT, they just mean local operators. So in this sense, I can call some scalar field phi a field, but a partial phi is some other field, as you probably know that it's the descendant of phi, if phi is a primary. And you can even write some weird things like e to the I alpha times phi. That's also a field. So they are all different fields, because they are all different operators. It really just means something depends on locally on the position. Okay. So now we understand what are primary fields. Now I can recap. What we learned last time is suppose I have a primary field phi with a certain dimension. In this case, we do have a z and a z bar, and they give us two non-related algebra. So instead of using delta, which is the dimension of the operator, we'll say that we use h and h bar to say that this is the eigenvalue under L0 and under L0, and this is the eigenvalue under L0 bar. So since I mentioned L0 and L0 bar, the sum give you dilatation, so h plus h bar will give you the delta you are familiar with. But from now on, we're going to characterize our field with two numbers. And let's only consider scalars for now. Maybe in tutorial or homework you will see other field that has other spins. But let me just mention that H minus H bar will give you spin because L0 and the L0 minus L0 bar give you the rotation. And the spin is tell you how things transform under rotation. So this guy, and then if it's put in a new position, okay. Since I can't remember everything, let me just think about dilatation for a moment. So if this is the case, they get dilated, the correlation function must be be dying. So this should be the correct transform. And now I can just say, let's write down how this thing transform under a general transformation, which is just the holomorphic transformation. Then you get a lambda. So df, dz, so the minus h, df bar, dz bar, to the minus h bar. And this part should be the same. Okay. So the primary field is defined as if some operator transform like this under a holomorphic, that is under the local conformal transformation, then it's known as a primary field with conformal dimension HH bar. Okay, so since we're in 2Ds, we have to emphasize if Fz equals anything, then it's a true primary field. And then if this guy only works globally, it's known as the quasi-primary field. And at some point, tomorrow or the next tutorial, we'll find out the quasi-primary fields are very interesting. A very good example is our energy momentum tensor. They're actually quasi-primary. Okay, so that's just the definition. And let's further define something called a chiral field. Chiral field just say, look, it's very hard to write down. It's not hard, but it takes time to write down the holomorphic part and the anti-holomorphic part. And what if the phi z only depend on z? That would be not nice. And if it is not nice, we'll call it a chiral field. It just means your field or operator only depends on z and doesn't depend on z bar at all. Such things exist. And the anti-chiral field is just the ones that only depends on, it's something that only depends on z bar. So from now on, we'll just focus on chiral quasi-primary field. And then you can just imagine that the anti-holomorphic part would work exactly the same way with everything has bars on it and so on and so forth. Okay? So what do we know about these primary fields? If you have participated in the tutorial last Thursday, you'll realize, well, these guys are really nice. I can immediately write down their correlation function. So the 2-point correlation function is given by z minus w to power 2 h1, because they disappear if h1, h2 are not equal times some normalization constant. Right? You shouldn't be surprised by this. You have did that yourself. Okay? And then 3-point function is something h1. Okay. The location would be z1, z2, z3. I'm just not writing them. And it should be like z12, which is defined by z1 minus z2. to some power, which is h1 plus h2 minus h3. And there were two similar terms, and they come with a structure. You have also done that into. And then if we go n-point function, okay, let's go for 4-point function. Since then, it's something like this, but then you have something depends on cross ratios. Remember the cross ratio? There's just one catch, is that you can, if you just multiply this guy all out, you realize there's a fun fact in 2 dimensions. Close enough. So remember your cross ratio is something like this divided by this and this divided by that. But we have this fun fact. You just substitute this. It's like 2 lines. You realize this is true, which means we only have one cross ratio. Okay. So that's what we learned last time. And then this afternoon, we're going to show that, again, I'm silly. Show again that conformal symmetry means energy momentum tensor is traceless, which tells us if you do it in the complex point, you have TZZ bar just disappeared. And even better than that, if you look at the TZZ, it only depends on Z. If you look at TZ bar Z bar, it only depends on Z bar. To realize energy moment tensors actually have two. So remember that it has like 3 entries, one disappeared. And the other one is one chiral field and one anti-chiral field. And tomorrow we'll study this guy for a whole class. And hopefully land on Virasoro algebra. Okay. And 4:15 tutorial.